Alright, in this activity we're going to go ahead and we're going to discuss Cascade control with the Temperature Control Lab unit. We've talked about feed-forward control. Cascade control is a little bit more nuanced. So we'll first design a Cascade controller. Right here, design. Then we'll go ahead and tune it. We'll look at the constants we'll need, and then we'll test it by actually implementing it with the Temperature Control Lab. Process is pretty similar to what's been going on. So here's the we're going to be controlling temperature 2. So I'll go ahead and get out my temperature 2 is going to be the controlled variable. Q1 is going to be what we are manipulating though. And we'll have a temperature 2 set point. So we'll measure the air relative to what temperature 2 is. And from that air, we need some way to control Q1 in order to change T2. So let's go ahead and think about how we would do this. I'll take off my pen real quick. Let's just draw this right here on the screen. Shouldn't be too bad. So if we think about our control blocks, we have our controller, we have our process, we have the measurement, and then let's go ahead and draw it. So we have right here is the set point. It's going to come here where it's going to be compared with the actual measurement. This is T2. And from those we get the error, E. That's going to go to our PID, which will then output some Q1, which will then come over here from the process. That's a bad process. From our temperature control lab, our Q1 will then go into some T2, which will then, this is a sensor. So the point here is this is how a normal PID control works. Now let's think about how this would work with Cascade control. So we'll go ahead and reset the pen real quick. With Cascade control, we have two different nested control loops, is how you could think of it. So let's just think through again how we're doing this. What we want out is T2. What's coming in is set point for T1, or sorry, T2. And so let's think right here. Right here, we're going to be comparing the measurement for T2 and the actual T2. So we can go ahead and we can draw this portion of the control loop pretty easily. Let's just leave room in the middle. So we'll say that's the T2 sensor. Now, instead of thinking of this in terms of just changing heater 1, what we can think of is from this we're going to have the error, and we'll do E2 for the error of temperature 2. Now what's going to happen is that's going to go into some PID control. We'll call that PID 2. Because what's going to come out of this is instead a set point for set point temperature 1. So instead of controlling the actuator itself, we're going to control the set point of temperature 1. That will then be compared in a similar way. This is a minus right here. That will be compared. So then from the set point, what we'll have is we'll have error 1, so error of temperature 1, which will then go into PID 1. From that, we will get a Q1. And from that Q1, it's going to go to our temperature control lab. From our temperature control lab, we will get an actual T1. And from that T1, we'll then have just the physical processes which will cause our T2. Now once we have this T1, this will come back. This is the information flow. And this right here is sensor 1. So the whole point here is that we are controlling temperature 2 by manipulating the set point of temperature 1, and then we control temperature 1 to reach its set point using the actuator Q1. This allows us to, this is cascade control. Some of the benefits are that we may be able to achieve finer control, and we may be able to kind of understand a little bit better the dynamics of what is going on by actually looking at the system a little bit better. So that's how the system is going to work. Let's kind of compare how this will work with just a PI controller for just one loop. That's how the PI controller would work. It would just be this outer loop, and then we'll go ahead and look at a PID Cascade controller. So let's go back to our live script now. So for standard PI control, we don't have constants for 1. We're only going to be manipulating the controllers for 2, the gain and the tau I. So let's go ahead, we'll play with these tuning constants, and we'll see the effect here. So as we increase the gain, not seeing too much an effect there, but that's because, so there you're seeing the increase in oscillation. If we change tau I, obviously increasing it's going to create control that's more conservative. Decreasing it is going to create more aggressive control with higher oscillations. So let's say tau I is about 110. And KC will make higher, and then we'll tune tau I. What I'm looking for is just minimizing this integral of absolute error, while at the same time not seeing a whole bunch of crazy control happening, and especially 80 is pushing it a little bit high, I'd say, for the temperature. So we probably need to be just a bit more conservative and allow that to ramp a little bit slower. That's more realistic rather than that very high ramp rate. It's probably less doable, and we still have a pretty reasonable integral of absolute error. That's how PI control would happen with this system. Let's look now at cascade control. Here we have to tune temperature controller 1. Here we go. So now we see an extra line up here. Let's go ahead and make this a little bit bigger because of all that's going on. So there's the heater values beforehand. Now we have 2 graphs. But the point here is that we have T1 set point as well as T2 set point. So up here we have the set point changing and how that affects our system. We'll notice, don't love the way the graph is being formatted right now, so let's go ahead. I'm going to just scroll down real quick to our plots and location. Instead of best, let's go ahead and say north, east for the legend for 1. Let's go ahead and try to run it again now. Okay, we're doing better. Still don't love now it's in the way of something else. It's in the way of us seeing kind of the end performance. But we can still characterize that first bit, and that's usually where most of the error is going to be. So we think through a cascade control. Again, what's happening is we have a set point change, and that set point change is changing our temperature 1, and temperature 1 is in turn, because of how close the heaters are, affecting temperature 2. As we change KC2, we'll see that's affecting the outer loop. That's affecting how the set point of the controller changes, or of temperature 1 changes. And if we change KC1, that will be how the performance changes, if you will, how temperature 1 changes in response to itself. Whereas KC2 is about setting the set points. So KCI is going to be a little bit more aggressive with the lower tau I. What we're really looking at is we're just trying to minimize this integral of absolute error. If we increase the KCs, lower the tau I's, you can see how now we have kind of some overshoot that's happening because of the outer loop and the integral of absolute error there. So we're just looking at the dynamics. That's one of the great things. So remember, we're at 355 now. With our Cascade control now, we're able to get down to 288, and we still have some overshoot right here that we can probably work out. Two. That's good. That's better. I apologize. We'll fix this this code right here, or make it so that it's less obtrusive to what we're looking at. The goal here was then just the two. In fact, let's just go ahead and we'll change the variables one more time within our plotting. Function. Here's the outer loop, and here finally is the testing stuff. Instead of having it, let's have the other ones come in at 300, I would say. Then IAE, it's actually okay. IE is plotted at 800, then we have some at 400, some at 600. We need to make them, I'd say, about 100 more spaced out. So instead we'll have some at 500 will be the next highest. We want 300 between it, so these will be at 200 then. Alright, one last time. Let's just do it. I like the way this is performing though. 2.2 is pretty good as far as performance. Okay, we're a little bit higher now because we changed the tau I. Seven, 2.6, 2.6. Much higher. If we go lower, do we get a better one? We start going up again. Okay, I want to say it was very close to here. There we go. Okay, we're going to leave it there. All right. Now we're going to go ahead and test it. So we have our tuning constant, 675, 5, and 150. So let's go ahead and implement those. KC1 was 6, then 75 for tau I1. KC was 5, and tau I2 was 150. Then we're going to put all, that's 120, 150. We're going to put all our coefficients in this coefficient array. We're going to initialize our lab. We're going to set the runtime to 15 minutes. Number of cycles is going to be some integer of that number, times the runtime, times the number of seconds in a minute. And then we'll get that number of loops. For each number of loop, we're going to create an array to store the values. And we're going to initialize it using lab.t1, so we get our actual initial temperature as the initial as the default temperature, we'll say. Then we create arrays not only for the set points, but also for the measured values. And then we do Q1 and Q2 arrays for those as well. We then have two loops. We have our main loop that will have the start time. We'll start a timer, and then we'll include the previous time, the derivative of error, the integral of error, and the integral of absolute error. We'll initialize those variables. Then we'll go ahead and with our loop, we will record the change in time. We'll record the delta time for our derivatives and other things, our integral especially. We'll then take the previous time as equal to t. Time I is equal to talk, where we're recording the time. We record the temperatures, and we record the disturbances. So what the change is from the deviation variable, if you would say. So d1 is equal to the difference between what it is now and 23 degrees Celsius, which is what we assume it to be. Another thing we could do is set it equal to the temperature at time equals 0. That would probably make it more accurate, more universally accurate, I would say. Then we have the integral of absolute error. For simplicity, what we have here is a PID controller for 1 and 2. You'll notice 1 outputs the set point at I, the integral of absolute error, and P. And then the second PID controller outputs the Q1, the P, and the integral of absolute error for, or the integral of error, I should say, for the inner loop. But one of its arguments is the set point that was set with the previous controller. That should make sense, hopefully. Finally, we write the output to the temperature control lab. You'll notice we're not changing Q2, and then we'll update our plot. So let's go ahead now, and I'll go ahead and run my code, and we'll observe the changes, or the performance. All right, here's our solution. So you can see the degree of tuning is actually quite nice. You'll see that our temperature 1 comes up. I wish it would have been a little bit over to the right for our, we'll go ahead, let's pull this out. So integral of absolute error, we're a little bit higher than what we would have predicted. That always ends up happening with our kind of just real life situations, but look how fine this control is because of how we're controlling this. Because we are focusing on temperature 1 and controlling that to the set point that we want there, temperature 2, and granted this is also due to just the fact that it's a little bit more loose, we're relying on the convection to get the heat to temperature 2, but that stays within the set point very well. You'll see we have, again, the whole concept here with Cascade control is because of the difference between temperature 2 and where it wants to be, the first outer PID controller sets the set point for temperature 1. Then the second PID controller sets how much heater should go to heater 1 so that temperature 1 goes to where it needs to go. Then heater 1 is adjusted, and then at each iteration, I should say, the set point is adjusted, and in turn the heater setting is adjusted for temperature for Q1, and we're able to keep T2 right along that 40 degrees Celsius line. And over 15 minutes, we have an integral absolute error of 2,880 degrees Celsius seconds, which is pretty good. Again, that's over 15 minutes, and you look at a lot of that's coming from this area right here where we're just trying to get it up to near the same time. So there we go. There's our activity, and I hope you've enjoyed using the temperature control lab in this course.